Okay, so hi guys. In this video, we're going to finally be looking at the applications of integral calculus. And one of the things that they love to ask you about is the area under the curve. So let's say we had this curve over here, which is y is equal to x squared plus 3. Or we can even write that as f of x is equal to x squared plus 3. And as you can see, this is obviously the y-intercept. And let's say they wanted us to find the area underneath the curve between the x-axis and from x equals 2 to x equals 8. So if we were to write that out, it would be, and of course this is the x-axis and this is the y-axis. So it would look like we'd have to find this area, this shaded area. Wait, let me draw that in a different color. It looks like it'll be that area. So to find that area, of course we need to use integration. So in the first video or so of where I was talking about integration, if we were finding the area underneath this curve, we'd break this up into many rectangles. And they would slowly get smaller and smaller. So that these spaces over here, wait, I'm going to color it in a different color. These spaces over here get smaller and smaller, and you have a greater approximation of the area. Whereas you have a limit to the area and the width of these rectangles, where they crawl towards 0. So in this case, the way you'd evaluate this, where you're having two regions that you're binding this integral with, is you would first find the integral of f of x, so integral of f of x, and then you would do the integral of f of x from the higher bound minus the integral of the lower bound. And this would essentially equal what we're trying to find in the first place. If we were to write it as one integral, this is our problem. Because it's asking us for the area in between 8 and 2. And if we do this, let me just explain how this works. So finding the area between 8 and 0, we'll find the area of this blue part here, but also this part over here. And finding the area of with the 2 and 0 is just this part over here. So when you subtract it from each other, you get rid of the red part, forming just the blue part area. And we can actually evaluate these on their own. So how would that work? Well, we first find the integral of f of x, so that would be 1 over 3 x cubed plus 3x. Not really going to go into that. Of course, there's a plus c, but I'll explain why that's not relevant. So now you'd sub it into this formula. You get 1 over 3, and then here, for x, you would substitute this bound over here. You substitute the 8, and similarly, you do it for 2 here. So wherever there's x, just substitute 8. So 1 over 3, 8 cubed plus 3 times 8 plus c minus, and then we'll put this in brackets because then the signs will change. 1 over 3, 2 cubed plus 3 times 2 plus c. And then the important thing to notice is that there will be a sign change. So it's quite clear that with this sign change, we will eventually lose the plus c. So let me just show you how that works. So that'll become 1 over 3 times 8 cubed plus 3 times 8 plus c minus 1 over 3, 2 cubed, and then also minus 3 times 2 minus c. So the c's cancel out. So you really don't even need to add the plus c in there. And now, if we work this out, so 8 cubed is, let me just use my calculator, I think it's 256. Oh no, it's 512. So 1 over 3 times 512 plus 24 minus, then 2 cubed is 8. So 8 over 3 minus 6, which is equal to, so 512 over 3 is 512 over 3 minus 8 over 3, because we're collecting the like denominators, gives us 168 plus 24 minus 6. Let's move this down, which gives us 168 plus 24 minus 6 gives you 186 units squared. So that's the area underneath the curve x squared plus 3 in between the x-axis and these two lines. So the blue area basically is 186 units squared. And since it's just on a coordinate plane, I would use unit squared as the default units. Alright, so let's do one more problem together. And so then you guys can kind of get the hang of it. So our final problem will be finding the area bounded by the curve f of x equals 4 of x, the x-axis x equals 3 and x equals 5. And as you can see, I've drawn a little diagram here to assist us. However, if you want to do this on your own first and try it out, you can. If not, or if you're still not too completely comfortable, you can follow along with me. So pause the video if you want to try it now, otherwise we're going ahead. So this is quite similar to the other one, except sometimes they may not give you a diagram. So it's important to check where the curve is, because if it's under the x-axis, we work a little bit differently. However, since in this case it's not, we're going to do the same thing. In future videos, I'll go to into if it's below the x-axis or if it's bounded by the y-axis and all that kind of stuff. So for now, no need to worry about that. So in this case, we first have to integrate f of x before we do anything further. So we know that 1 over x when integrated is ln x. And so that means that the integral of f of x must be ln of x. And obviously it's the absolute value of x as we had mentioned. The reason it's not going to be ln 4x is because when you differentiate ln 4x, it gives you 4 over 4x, which results in cancelling out to get 1 over x. So that's why we can't do ln 4 over x. In this case, though, ln x becomes 1 over x, so 4 times 1 over x is 4 over x. And we have the plus c, but we don't need it as we just realized from the last example. Now, the next thing we have to do is construct our equation. So what we're going to have to find out is the upper bound's 5, the lower bound's 3 of f of x. And we have to realize that this is equal to 5 times integral, the upper bound 5 of the integral f of x minus, and then 3, 0, f of x. So let's start off by evaluating this equation using what we know. Well, we know it's 4 ln x, so we must be able to recognize that it's 4 ln, and then it's going to be 5 because we're substituting the upper bound in, minus, and then in this case it's going to be 4 ln 3 as we substitute the lower bound in. So that makes it pretty simple, but now we need to write it in a more specific, more simplified version. We will write it as one term, so it becomes ln 5 to the power of 4 minus ln 3 to the power of 4, which gives us, and then let me just do 5 to the power of 4, equals ln 625 minus, and then 3 to the power of 4, 81, ln 81. Which means, using law of logarithms, it's 625 over 81, which is equal to, and then 625 divided by 81. It's still the same. It can't be simplified further. So if we were writing it very specifically, this would be how we write it. However, if we wanted to find the exact value, we just evaluate ln. Well, not the exact value, but to a decimal place. That would just be ln 625 over 81, which gives us roughly 2.04 units squared. Unless they specify different units, always use units squared, it's just safer. So this one wasn't too bad, and that's how you do it. But this is probably the easiest part of the area under the curve. There are some other problems where you might have to find areas between curves, or with the y-axis. With the y-axis, one's quite cruel. And then it could even be where some of the curve is below, some of it's above, or some of it's completely below. So you need to be able to adapt to that, and we'll go over that in the next few videos. So thank you so much for watching, and see you in the next one.